Hello and welcome to the final part of Lesson 2. Up until this point, we've reviewed solving the equations of motion for a Newtonian fluid with the intention of calculating parameters such as a pressure drop, or perhaps a shear rate profile, or perhaps a state of stress. We've acknowledged that Newtonian fluids are rarely encountered in polymer processing operations, but we'll be seeing how to extend these calculations to more useful fluid rheologies in the lessons that come. What we're going to do in this final part of Lesson 2 is examine flows from the standpoint of the conservation of energy, which will give us another tool with which to calculate pressure drops. You will almost certainly have come across this approach before in undergraduate courses, as you will have encountered Bernoulli's equation. So we're going to start by reminding ourselves of what Bernoulli's equation describes, and then take a very careful look at how we use conservation of energy for different flow regimes and for different fluid rheologies. So, when you've heard the phrase Bernoulli's equation before, it probably would have been applied to a system as follows. You might, for example, have two reservoirs of fluid at different elevations connected by a piece of pipework, and that pipework typically will have bends and fittings in, fittings such as valves or T-junctions or diameter constrictions, something along that nature. And typically what you'd do is you'd take a streamline from the first reservoir to the end of the pipe, and you'd take that streamline far enough back into the first reservoir to say, at this point my fluid is stationary, I can set V1 to 0, perfect. And then what you'd do is you'd apply Bernoulli's equation along that streamline. And Bernoulli's equation has a number of terms in it. It has a kinetic energy change, it has a free enthalpy change, it has a potential energy change, and it has frictional losses, and all of that summed together to give you an idea of the energy input required to make that flow happen. So, you might be used to seeing this written as a half rho v squared for the kinetic energy change, but just bear in mind, for this formulation, I've just divided through by density. Let's take a look at the units that gives us. So, if we look at the simplest unit there, that v squared, that's meters squared per second squared. That's actually the same as joules per kilo. And if you don't believe me, we can think about it. So a joule is a force times the distance. A force is a mass times an acceleration. So we've got mass times acceleration times distance over mass. So we've got acceleration times distance. So we've got meters per second squared times meters, which gives us meters squared per second squared. So Bernoulli's equation written in this form allows us to work out the energy change per unit mass of fluid. So let's have a very careful think about that kinetic energy term, because almost certainly you'll be used to seeing it written a half rho v squared. Okay, I've divided through by rho, so it's a half v squared here, but that factor of a half. Now, when you see this written for different fluid rheologies, or even different flow regimes of Newtonian fluids, that half may not be there. And you may think, oh, that's a mistake. We can't have that. Actually, no, I'll show you that actually it is consistent to sometimes have that half, to sometimes not have that half, or to have sometimes another fraction there. So let's look at a little more detail what that kinetic energy term has in terms of its origin. One of the best and most thorough resources for this is Bird, Stewart and Lightfoot's transport phenomena. Of course, Professors Bird, Stewart and Lightfoot were all professors at the University of Wisconsin-Madison, and their book on transport phenomena has completely changed how we teach many aspects of chemical engineering. So they write that kinetic energy change is written as follows. It's the change of a half of v cubed in pointy brackets divided by v in pointy brackets. Now, v to the power n in pointy brackets is written as this fraction concerning double integrals. Let's look at the denominator first. The double integral there is from 0 to 2 pi, from 0 to r, of r dr d theta. And if we work that out, we'll see that that first bit, that r with respect to dr, gives us r squared upon 2. And then the second bit gives us 2 pi theta, if we've got a circle. And that effectively just gives us pi r squared. It gives us an area. So let's now focus on the numerator with that double integral. And we can see what we have is the angular component, that 0 to 2 pi d theta, gives us 2 pi. And then we're left with an integral between 0 and r of the radius times how the velocity field changes with radius raised to the power n dr. So this is quite interesting because if n equals 1, that collapses to a familiar expression, which is the volumetric flow rate. And if we divide the volumetric flow rate by the cross-sectional area, we get the average flow velocity, v in pointy brackets. Okay, fine. Now, let's look at the kinetic energy term again in light of that. So, Bird, Stewart and Lightfoot write the change of 1/2 of v cubed in pointy brackets divided by v in pointy brackets. And we can now write that in terms of that integral there in the numerator, 2 pi 0 to r of r times v cubed dr divided by pi r squared times v in pointy brackets. Now, we can evaluate that and write that as follows, and we'll evaluate that for various flow profiles in a minute, but that is the important point. Those two words, flow profile. This integral in the numerator of the kinetic energy term has a term of v of r cubed. And so the velocity profile in the flow matters when we're working out the kinetic energy change. The reason why you've always used a half is because for turbulent flows, we're assuming plug flow. And we'll discuss that more in a second. So, our first term of Bernoulli, that kinetic energy change term, can actually more accurately be written as follows. So let's see what it is for a laminar Newtonian flow. So we know that for flow down a pipe, in laminar flow, with a Newtonian rheology, the velocity will be a parabolic function of radius. So there we have v is delta p over r squared over 4 mu l, 1 minus r squared over r squared. That's a bit of a mouthful to keep writing on the board, so I'm going to abbreviate this as alpha 1 minus r squared over r squared. And alpha, of course, has a physical meaning here, because when our radius is 0, when little r is 0, our velocity equals alpha. When r equals 0 on the centre line, which is where our maximum velocity is, so alpha in this expression is just our maximum velocity, okay? So, let's substitute that expression for v into the kinetic energy integral that is proposed by Bird, Stewart and Lightfoot. I'm not going to go through the details of the integration. If we make that integration, we get the following expression. And if you don't believe me, go away and prove it yourself. Alpha cubed r squared over 8 is what results from that integral. And we still retain in the denominator v in pointy brackets r squared. So the kinetic energy term for a laminar Newtonian flow is actually alpha cubed over 8 divided by v in pointy brackets. And v in pointy brackets is simply the average velocity. It's q divided by a. So for a laminar Newtonian pipe flow, we also know that the average flow velocity, as well as being volumetric flow rate divided by area, is the maximum flow rate divided by 2. That's the same as saying alpha divided by 2, because alpha was our maximum flow rate. So, if we rearrange that in terms of alpha, alpha is equal to 2 times v in pointy brackets. If we cube it, it's 8v cubed. So we get 8v cubed over 8v, which just simply leaves us a term in v in pointy brackets squared. So the whole point of these last few pieces on the board were to demonstrate that the half term that you see in the kinetic energy term in Bernoulli is not always there. It is there for turbulent flows, but for laminar flows it's not. So for laminar Newtonian flow, the first term in Bernoulli, that kinetic energy term, is simply the difference of the squares of the velocities at each end, assuming that we're dealing with the equation that's been divided through by density. It is not half of that difference. So let's just write a more general version of Bernoulli down that we can now use in different situations. Instead of writing a half v2 squared minus v1 squared, I'm going to write 1 over beta v2 squared minus v1 squared. Now, for laminar Newtonian flow, beta is equal to 1. We've just proved that. For the turbulent flow of any rheology of fluid, what we're saying is, well, turbulent flow gives us a kind of plug flow-like profile. So the change of a half of v cubed in pointed brackets over v in pointed brackets, well, if v in pointed brackets is basically equal to v because it's plug flow, that just gives us a half v squared, which is where that half factor comes from. So turbulent flow of any rheology, beta is equal to 2. And for laminar power law flow, beta is a function of our power law index n, as written on the board there. So the take-home message here is be careful to choose the right kinetic energy term when using Bernoulli for laminar systems. Very often, in actual fact, the kinetic energy contribution is negligible, but there may be situations where it is not. And so at that point, it's even more important to have the right terms of the right magnitude. Okay, so let's think about how we might apply Bernoulli now. So typically in the past you might have been, for example, evaluating frictional losses for straight pipes. So F here, sum of F, is the sum of frictional losses. And that includes pipe loss fittings and pipe loss friction, and includes fitting friction. So let's examine the first of those, which is pipe friction. So the friction due to pipe flow is written in terms of a fanning friction factor, CF. Bear in mind that there are two friction factors, but we're using CF here. So my friction due to flow is 4CF L over D times a half V squared. Remembering, of course, we've already divided through by density. And we can do a quick unit check, and that gives us units of meters squared per second squared. So that's fine, it's consistent. And we can evaluate that fanning friction factor for laminar Newtonian flow. It's simply 16 over the Reynolds number, where Reynolds is rho d v over mu. We can also evaluate the fanning friction factor for turbulent flow of Newtonian fluids, and there on the board is an expression implicit in CF that allows you to do that, so that will require numerical solution. Moreover, we can also evaluate the fanning friction factor for generalized Newtonian fluids. So for power law fluids, the fanning friction factor in laminar flow is 16 over the Reynolds number, the power law Reynolds number. And the power law Reynolds number can be written as I've put there on the board, and now it involves the power law index n and the consistency index k. So it's different in form to the Reynolds number you may be used to using for Newtonian fluids. You can, of course, get turbulent flow of power law fluids, and there is an expression that allows you to evaluate the friction factor for the turbulent flow of a power law fluid. Again, it's implicit in CF and requires numerical solution, and the rheology features because it is also dependent on the power law index n. Okay, so we're getting to a more general version of Bernoulli. If we're going to use Bernoulli for varying flow situations, we need to be able to discriminate when the flow is laminar and when the flow is turbulent. And so we use the Reynolds number to do that. And as a reminder, laminar flow for Newtonian fluids in pipes is typically below about a Reynolds number of 2100. Turbulent flow for Newtonian fluids in pipes is typically above Reynolds number of 4000, and there's that transition region in between. And bear in mind that turbulence can be tripped a little earlier than 2100 Reynolds number, depending on the external environment. Shocks, mechanical shocks, for example. That's all straightforward enough, but if we think about generalized Newtonian fluids, we also have laminar and turbulent flow, and we need to be able to evaluate the transition between them. So for power law fluids in pipe flow, we have a critical Reynolds number, where is laminar below that critical Reynolds number and turbulent above that critical Reynolds number. And for power law fluid, I've written on the board there an expression which allows you to work out what that critical Reynolds number is. And again, it's all phrased in terms of the power law index n. So we've talked about frictional loss in pipes. What about frictional losses in fittings and bends? Because typically you're unlikely to have just a simple straight pipe. So that also comes into that parameter capital F there. So capital F is going to be the sum of the frictional losses due to the pipe and the frictional losses due to the fittings. And when we're thinking about the fittings, what we have are a sum of loss coefficients, K, multiplied by V squared upon 2, because we've divided through by density, ordinarily rho V squared upon 2. Again, if we just do a quick unit check, the frictional loss due to fittings has orders of meters squared per second squared, so we're dimensionally consistent with the rest of the equation, so that's good. Now, if we're dealing with the laminar and turbulent flow of Newtonian fluids, and for relatively high Reynolds number flow of power law fluids, say above 500, that fitting coefficient K is simply the catalogued fitting coefficient that you'll find in any tables of losses. And we'll have a look at one of those tables in a minute. However, if you've got a low Reynolds number flow of a power law fluid, there's a correction factor that needs to be applied to Kf, and that is 500 divided by the power law Reynolds number. So there on the board I have put a table of loss coefficients, Kf's, and we can see that they're different for different types of bend or different types of fittings. So you've got long radius bends and short radius bends that are either 45 degrees or 90 degrees. You've got T-junctions and 180 degree bends and couplings and unions. All those good things that you're likely to see along a piece of pipework. I haven't included any valves because I've said you're unlikely to encounter those in a polymer processing operation, because all that will happen to them is they'll probably get set solid in polymer when you cool the line down. So, I think what would be a good idea now is to give you a couple of examples of how to apply Bernoulli's equation in a more general sense to a flow scenario. I'll start with a Newtonian flow scenario and then move to a power law flow scenario. So, the flow scenario is thus. We've got two reservoirs of fluid, looks a bit familiar, and what we're going to do is we're going to move fluid from reservoir 1 to reservoir 2, but reservoir 2 is more elevated than reservoir 1, so we're going to have to pump the fluid. Okay, so what we're going to do is we're going to take a streamline from reservoir 1 all the way through to the end of the pipe, and we're going to take that streamline far enough back into reservoir 1 such that we can assume that the velocity is negligibly small, and we'll call it 0. We're also going to assume that the pressure at that point in the streamline is P1, and the pressure at the exit of that streamline in position 2 is P2, and they're both open to atmosphere, so P1 is equal to P2. Let's set some data for this fluid. I'm going to flow this fluid with a velocity of 1 2/3 meters per second. The fluid is going to have a density of 1250 kilos per cubic meter and a viscosity 340 times that of water. The pipe diameter is going to be 34.8 mil, nearly 35 mil, and the total pipe length is 10 meters, and the elevation change is 5 meters. Okay, so there are my assumptions that I've made due to the placement of the streamline, V1 equals 0, and atmospheric pressure at both ends, P1 equals P2 equals P atmospheric. So let's now work out what the Reynolds number is. I'm not going to go through that calculation. I'm assuming you're happy with that. The Reynolds number is 212, so we have a laminar Newtonian flow. Our friction factor will be 16 over the Reynolds number, and that's what gives us 0.0755. And for laminar Newtonian flow, beta equals 1, which is that factor that pre-multiplies the kinetic energy term. So let's now think about Bernoulli's equation there at the top of the board. 1 over beta, difference in velocity squared. 1 over rho, difference in pressure squared, that's 0. G delta H, well that's my elevation change, and the sum of losses. So let's start with the sum of losses. So let's deal with the pipe losses first. So I've got 4 times CF times L over D. 4 times 0.0755 times 10 over 0.0348. That's 4 CFL over D times a half V squared. And the length is the entire length of the pipe. I'll add on the bends in a minute. Okay, so that's the pipe loss. Now let's think about the fittings loss. We've got laminar Newtonian flow, and so all I need to do is to use the fittings coefficients as they're stated in the tables. And for a short radius 90 degree bend, that fitting loss is 0.75. And so I have 4 bends. I got 4 times 0.75 times a half V squared. So my pipe friction loss plus my friction fitting loss gives me just shy of 124 joules per kilo. Okay, great. Now let's look at the other terms in Bernoulli. That kinetic energy change, beta equals 1 laminar Newtonian flow. The velocity change is 1.66 squared minus 0 squared. Okay, which actually is a very small number compared to that 123.6. So that kinetic energy change is effectively negligible. Let's think of the potential energy change. We've got gravitational acceleration of 9.81 meters per second squared and an elevation change of 5 meters. And then that 123.6 is our total sum of frictional losses, which gives us 175.4 joules per kilo of energy input required to make this flow happen. So that's very useful to know, because the pump pressure rise we can work out using that energy input figure. It's the energy input times the density. So rho times W, where W is the sum of all these terms in Bernoulli, is 219 kPa, about 2.2 bar. So that's a very quick way to give a very useful result about some pumping pressure required to take a fluid from point 1 to point 2 through a pipe that's got bends in it. Let's have a look at the same example now with a power law fluid. We've got the same system configuration. We've still got 2 reservoirs and an elevation change of 5 meters. We're still taking that same streamline from point 1 to point 2. So it's far enough back into point 1 where we can assume the velocity is 0, and we're assuming that P1 and P2 are equal pressure. They're both atmospheric pressure. So a lot of the data for this fluid is the same. It's still flowing at 1 2/3 meters a second, and it still has a density of 1250 kilos per cubic meter. What's changed, however, is the rheology. We have a power law fluid. I've got a consistency index of 5.2 Pascal seconds to the 0.45, and my power law index is 0.45. Pipe diameter is the same, the total pipe length is the same, and the elevation change is the same. Okay, so there is a statement of the assumptions that I've made. There at the top of the board is Bernoulli's equation, and now we have to think about beta, Reynolds number, and fanning friction factor. So, using the expressions that I've shown you earlier in this part of this lesson, we can work out that the Reynolds number is 365, one for every day of the year. 16 over the Reynolds number gives us our fanning friction factor, which is 0.0438. Furthermore, we can now work out what beta is going to be for my laminar power law flow, because our Reynolds number now is below 500. Beta is 1.2. So we've got 1 over 1.2 times the square of the difference of the velocities. So let's again look at the frictional losses first. So the pipe loss is going to be 4 times Cf times L over D times a half V squared. The only thing that's changed here compared to the previous example is the value of the fanning friction factor. It's now 0.0438. So that's what's written there on the board. 4 times 0.0438 times 10, pipe length, over 0.0348, pipe diameter, times a half V squared. Now let's think about the frictional loss due to fittings. We've got a slight complication this time because we realise that my power law Reynolds number is 365. It's below that 500, so we need to correct the fittings by a factor of 500 divided by Reynolds number. And so we've got 4 90-degree short radius bends. A short radius bend of 90 degrees has a friction coefficient or a loss coefficient of 0.75. And there's 4 bends, so 4 times 0.75 takes into account the number of the bends. That 500 over 365 is the correction required due to this lower power law Reynolds number. And then it's times a half V squared, a half times 1.66 squared. And we can see that the sum of all the frictional losses now gives us about 75 joules per kilo, which is a good deal less than what we saw last time. So let's evaluate the remaining terms in this equation. Kinetic energy change, 1.66 squared minus 0 squared over 1.2. Elevation change for potential energy, 5 times 9.81. And then our frictional fittings, our frictional losses, come as 75.1. So the total work required to make this flow possible is 126.4 joules per kilo. Multiplying that up by density, that gives us a calculation for the pressure rise across the pump, which is going to be 158 kPa, or about 1.6 bar. So there you have it. Okay, let's recap some key points. We've spent this final part of lesson 2 revisiting Bernoulli so we can calculate pressure drops in pipe flows. For laminar flows, we have to be very careful as expression looks a bit different from what you've seen before, that kinetic energy change term. So we can calculate different values of that term for Newtonian and for power law rheologies, but as we've seen, typically that kinetic energy term doesn't contribute a great deal to the end result because our flows are so viscous. You've got to have a little bit of care when calculating Reynolds numbers, as it will change between a Newtonian and a power law, and the power law Reynolds number is evaluated as I've shown you previously. Also, if we're thinking power law fluids, we need to work out what that critical Reynolds number is for flow transition from laminar to turbulent, so again we have to be a little bit more careful. And just a final disclaimer is the result, of course, is an estimate for a more complex rheology. We haven't included any physics to do with time dependency or elasticity, but coming full circle is back down to the type of problem you're trying to solve. What accuracy of answer do you need, and what is fit for purpose?